Hello everyone and welcome to the latest. Today we'll be taking a look in 30 short minutes at the topic of formulation for inkjet printing. Today, your speakers, I'm Dr. David Calvert. I'm going to be your guide for today, and our main speaker today will be Dr. Jim Bullock, who will be taking you through an agenda which you will see on the next slide. The agenda today will start off with the obvious question about why would you choose inkjet printing, and then how does it work. Obviously, if you're doing formulation, you need to know what's in an ink, and one of the key properties in all formulations, how do you stabilize them. We'll be taking a brief look at performance testing and then a summary and learning more. This webinar is being recorded and will be made available to yourselves and your colleagues and everybody who's registered afterwards. You'll be sent a link to the recording and you'll also be able to download the slides. You are being muted. If you wish to ask questions, then please use the question function in GoToWebinar, and the webinar will last approximately 30 minutes. Before we start, a little bit about ourselves and iFormulate. We're a company founded by Jim and myself, who have both got close on 25 years experience in the formulation industries. We've been in business for just over 3 years, and we bring our own experience and knowledge to customer problems together with those from a range of associate partners who tend to complement our own activities. We divide our activities into 3 business areas. At iFormulate Consult, it's straightforward business to business, and we carry out innovation and technology consulting, mainly in the areas of formulation science and technologies. In iFormulate Strategic, we have carried out a range of different assignments and strategic projects in the area of formulation science and technologies. These have been for sector bodies and associations such as the Knowledge Transfer Network, the National Formulation Centre and the Royal Society of Chemistry. Today's webinar is a part of our iFormulate Skills strand, where we promote training courses and programs which are either under our own banner or maybe in partnership with third parties. And this one is our iFormulate Skills, and you'll see further details on our website. Before we get into the meat, we need to acknowledge a lot of the material today came from one of our associate partners, Mark Holbrook, who has an awful lot of experience within the inkjet, and he'll be joining Jim on the 9th of June to deliver inkjet formulation fundamentals. There are more details about that workshop via the web link shown and at the end of the webinar. In the webinar we will be using brand names, but of course, as I always say, there are other products available and we are not endorsing the products that we mention. So, as we said, the first obvious question when you're thinking about this is why would you choose inkjet printing? And really, inkjet printing has come with the digital revolution and has rose in prominence with that. It offers speed, it offers flexibility and convenience, and obviously digitalization allows you to customize your product. Perhaps with all of those customization has come a great improvement in quality and an integration with digital imaging and design. Now, although we'll be talking a lot about imaging and reprographics, actually inkjet printing can be used in other areas such as electronics, pharmaceuticals, diagnostics and additive manufacturing, which is commonly known as 3D printing. So when you've decided you wish to choose inkjet printing, you're off to know how does it work, and at this stage I'm going to hand over to our main speaker, Jim Bullock. Over to you, Jim.
Thanks, David. So let's start with a brief look at how inkjet printing works. And for those of us who think we remember inkjet printers being developed in our own lifetime, it comes as a bit of a surprise that the technology's got rather a more ancient history. So in 1749, the French scientist Abbé Millet demonstrated that you could shift a stream of droplets by using static electricity, and took over 100 years before William Thomson invented a practical recording device using the first continuous inkjet printer. So again, a stream of ink was deflected by electrostatics to record telegraph messages, and if you were very skilled, you could probably start to decipher those wiggly lines that you see at the bottom of the slide there. So 1858, but it was much later that inkjet technology came into most people's consciousness. And in fact, these days there are two main families of inkjet technologies. We won't be able to go into detail on all of them, but we'll touch on the two families, continuous and drop-on demand. In continuous technologies, a stream of droplets is deflected, rather as William Thomson used to do, with an electrostatic field, and that continuous stream of droplets can be deflected to or away from the substrate, and ink which is unused is then simply recycled back into the reservoir and printed out again. So that's continuous technology. In drop-on demand, drops are generated only when they're required. And so let's look in more detail at those two families of technologies. Continuous inkjet printing. Ink is pumped through a small nozzle, and as it's pumped through that nozzle, it atomizes, it breaks up into droplets, and this uses a phenomenon known as the plateau-Rayleigh instability, which is the property of liquids which tend to minimize their surface area, and you may see that more commonly at home with a dripping tap, for instance. So minimizing the surface area means forming droplets. Droplet deflection is achieved by applying an electrical charge to those droplets as they emerge from the nozzle. So in the diagram at the bottom, you can see that ink is pumped through, it is broken up into droplets, vibration is applied, the droplets are charged in the charge tunnel, and then as they pass out through the nozzle, they are deflected by an electrostatic potential on the deflection electrodes. The droplets that are forming the image are undeflected usually and fall onto the drum to form the image. Those not required are deflected away and recycled. And in its highest resolution form, in the Hertz technology used by printers such as Iris and Stork, the droplet size can be as small as about 10 picoliters, and ink droplets are applied at a very high frequency, over 1 megahertz. The advantages of continuous inkjet printing are that it's a high-speed technology, and that's because of that high ejection frequency which we showed you there. So found an example here of a recent Videojet printer which claimed over 500 meters per minute line speed in marking applications. There's the flexibility to use both aqueous and non-aqueous organic solvents, depending on the type of ink that you want to use. And there's a very high drop velocity, which means that the droplet can travel a rather long distance from the head to the substrate, which can give you a little bit more flexibility there. The disadvantages are that, relatively speaking, compared with drop-on demand, the images are of lower resolution. There's a higher maintenance requirement. The fluids that you have obviously must be electrically chargeable. Typical uses for continuous inkjet are primarily in industrial and commercial printing. So industrial marking, for instance, where you want to apply a sell-by date or a lot number to food or drink packaging. It's used famously for marking eggs, and quite often also in textile printing. Moving on to drop-on demand technologies. In thermal drop-on demand, a resistor is used to heat the ink and produce a bubble which ejects a droplet. And so that heating element is switched on when a droplet's required, and that causes a bubble to force a droplet out of the ink reservoir through the nozzle. This technology is more commonly used for desktop, so-called small office, home office or SOHO applications, and for office printers, also sometimes in wide format printers. And again, this technology can be divided into at least two geometries, the so-called edge shooters, where, as you see here, the direction of the generation of the bubble and the direction of the droplet are 90 degrees to each other, or in a phase shooter where the resistor is behind the reservoir, immediately behind the droplet being ejected. So two different applications there. In piezo drop-on-demand, such as used by the Epson printers, piezoelectric crystals such as lead zirconium titanate deforms when you apply an electric field to it. And as it deforms, it squeezes the ink reservoir and forces a droplet out through the nozzle. And this is also used in desktop applications, but increasingly obviously in business and industrial and commercial applications. If you start to take apart a thermal print head, and here's an image of what happens when you take off the gold nozzle plate on a thermal print head, for instance, you can see an array of nozzles underneath that print head. And this gives you a clue as to how a high-resolution image is generated. If you go back about 20 years to the first Soho printers, such as the HP DeskJet, we may remember those operating in our offices, for instance. They had about 300 nozzles operating at frequency of 8 kilohertz, producing a droplet that was 35 picolitres in size. Image resolution standard then was about 600 dpi. 10 or 11 years after that, in the HP's Design Jet, the industrial printer, there was an array of up to 10,000 nozzles operating at 36 kilohertz, so a huge increase in terms of the frequency, and the droplet size down to 2 picolitres, producing an image resolution of around 1200 dpi. Most recent example here I found recently, just some description from the Canon website for their fine printers, thermal printers. We've got up to now a claimed resolution as 9,600 dots per inch, which means 6,000 nozzles in an area of only 20 by 16 millimeters. Droplet size, they're really tiny, 1 picolitre, which means that the droplet diameter is just over 1 times 10 to the minus 5 meters, so that's pretty small. Nozzle size 9 microns. So these are really small nozzles, and as we'll see later, that places some demands on the ink as you formulate it. So increase in resolution, decrease in droplet size, increase in the number of nozzles, increase in the resolution. In piezo inkjet, for drop-on-demand industrial applications, it tends to be favoured despite the higher costs. So the piezo heads are expensive, but they have advantages over thermal heads. They're more robust, giving you longer lifetimes. There's a much more controlled droplet formation process. There's a greater range of ink chemistries possible because you're not heating it. Heating can cause damage to the ink, and therefore piezo inks, you can be more flexible about your formulation there. And the ink head technology tolerates a wider range of ink physical properties. There are several different piezo modes, including, as we've seen before, the edge shooter. We've seen so-called piston designs, and probably the most significant different design for piezo inkjet is the ZAR shared wall technology, where you have electrodes on the wall of the reservoirs which apply a shear to the ink in the reservoir and squeeze the ink out of the nozzle, and the nozzle's facing towards you as you look at this diagram here. So that's the so-called shared wall, multiple array of nozzles with a piezoelectric material forming the wall of the nozzle. So what's in an ink? Well, first of all, to work out why you have certain components in an ink, it's worth looking at the demands placed on inks. And the printhead technology, as we've seen, places some demands on an ink, and here are some examples of those demands. So if you have a thermal head, then your ink needs to be stable to repeated heating cycles. If you have piezo or a thermal head, you will see that ink is sheared, and that ink needs to be stable to repeated shear cycles. Particularly in continuous applications, there's a danger of evaporation loss. You may need to protect your ink against evaporation loss. In all technologies, there's a risk of blocking of nozzles, so you'll need to consider that. For continuous applications, your droplet needs to be charged. In all applications, you'll need to be able to form that droplet repeatably and reliably. That's a function, as we shall see, particularly of rheology and surface tension. In all applications, you'll need to consider the materials of the printer. That's a particular factor to consider with the shared wall piezo design, where, as you can see, the wall of the ink reservoir is actually made out of piezoelectric material, which can be sensitive to aqueous inks. The end-use application also places certain demands on your inks as well. So in all reprographic applications, you'll need a consistent reproduction of color, hue and saturation. You'll need a good image resolution and a depth of color reproduction. You'll need fastness, very often, to light, to water, to touch, or to abrasion. You'll need to avoid color bleed from one part of an image to another. In industrial applications particularly, you'll need that ink to dry rapidly. Your ink needs to be compatible with the substrate, both in terms of appearance and mechanical stability. Your ink needs to have some affinity for the substrate, whether that be paper, textile, plastic, or whatever. And of course, apart from the end-use application, your inks need to be stable to being stored and handled under a wide range of conditions, as well as during the filling process. So quite a lot of demands there. So what does that mean has to go into that ink formulation? So again, for reprographics, you'll have a dye or a pigment on there. We'll come on to the choice of dye or pigment in a second. For pigment inks, you'll need a dispersing agent in there to disperse the pigment particles. That's usually a functionalized copolymer rather than some sort of classical surfactant. You'll probably need a wetting agent in there, a surfactant to control surface tension, a co-solvent if you have dyes to enhance the solubility of the dyes. You will probably need a humectant, which prevents the drying out of the ink, or make that crust that can form on drying more mobile. And it can also act to tune the viscosity of the ink as well. You may well need a penetration enhancer to enhance end-use application properties. A binder, example of where you might need a binder is if you're printing pigments onto a textile substrate. So you may well need a binder to enhance the affinity of those pigments for the textile substrate. If you have water-based inks, you'll probably need a biocide preservative in there. Because your dyes or your dispersing agents may be sensitive to pH, you may need to control your pH with a buffer. And of course, you have a solvent, which may be water, may be organic. So when it comes down to the choice of dyes or pigments, conveniently you have a number of properties here, and usually what's good for dyes is bad for pigments and vice versa. So quick definitions here. Dyes are soluble in the ink medium, whereas pigment particles are insoluble and therefore are dispersed in the ink medium. So dyes then are easier to formulate, they're soluble. Pigments are harder to formulate, they have to be kept dispersed and stable. Dyes tend to be bright, and there's a huge range of chemistries available for dyes, so you have the ability to tune the shade very, very precisely. Pigments can be bright as well, but the range of shades available is more restricted. Dyes tend to have lower color strengths. Pigments have a very high color strength. Dyes have a low risk of blocking your nozzles. Pigment particles have a higher risk of blocking your nozzles. Dyes can give you good rub fastness. Pigments don't have any particular affinity for most surfaces, and so the rub fastness tends to be poorer. Dyes tend to affect the gloss of the substrate rather less than pigments. But pigments tend to have better water fastness, light fastness, better penetration, better image quality, and a lower risk of chemical degradation, so there's some good reasons for choosing pigments as well. And again, because of the stability issue with particulates, then dye formulations tend to be rather better performing from a storage stability point of view. Let's move on to some of the choices that you might have in inkjet printing. So if you're choosing dyes, you will probably be choosing a disazo yellow, such as Direct Yellow 86. It's very soluble. You can see all those sulfonate groups on there. But it's also a rather large molecule, and that helps the substantivity, the affinity for the dye to the paper substrate. Magenta dyes, you may be choosing another azo like Acid Red 249, which has particularly good light fastness. For cyan dyes, Direct Blue 199, the copper phthalocyanine is probably going to be your direct blue of choice. That's not only cheap and water soluble and bright, but it also has very high light fastness, and that's the reasons why in many older inkjet prints on paper, the other colours will fade before the blue, so you may well see your image fading to a blue colour, where most of the dye that you've got left that hasn't faded is blue 199. For black, usually you have a dis or a tris or a tetrakis azo structure example here, black 19, which has good strength and water fastness. If you're choosing pigments, your choice may be for pigment yellow 155, which has good light fastness and is insoluble. You don't want solubility because solubility can give you stability problems. Pigment violet 19 might be your magenta of choice. The quinacridone family are very good in terms of their shade and their properties, their light fastness properties. You may need to blend those to get the shade that you require. There's more or less only one choice for cyan, and that would be pigment blue 15, again a copper phthalocyanine, which has a very good shade and light fastness, low solubility, relatively easy to disperse and stabilize in the formulation. And for the black, again usually only one choice, carbon black. There's a huge variety of grades and suppliers, and the purity of that carbon black is very important. You'll see many suppliers offering inkjet grades of carbon black. So those are your colorants, but there are some other components which are important. You have to consider their properties as well. So surfactants are used to control the surface tension of the ink. And for water-based drop-on-demand inks, you're normally looking at a range of 32 to 36 dynes per centimetre for your surface tension. Your surface tension is too high, then those droplets simply don't disengage. If the surface tension is too low, then those droplets will drip, and you get wetting of the nozzle plate, which is not what you want to happen. The surfactants need to act at a range of shear rates from very low shear, less than 1 per second in the flowing ink, up to 10 to the power 6 per second as the ink passes through the nozzle. So what's important here at these high shear rates is dynamic surface tension, and that means you need fast-acting surfactants. They tend to be rather small molecules so that they can get to the surface very, very quickly. You also need low foaming, and very often the surfactant of choice might be the acetylenic diol family of surfactants, such as surfenyl from Air products. So they have that high dynamic surface, that low dynamic surface tension to enable droplets to be formed rapidly. Some other components you may need to consider. You may need to adjust the viscosity of the ink. Again, for typical SOHO, small office, home office printers, you'll be looking for almost water-thin inks, 1 to 3 centipoise. Industrial print heads running at higher temperatures can run around 10 centipoise. If your viscosity is too high, the nozzles will refill too slowly. If the viscosity is too low, then the droplets may break up. Sometimes those components you've got in there, like the humectants and so on, will give you a viscosity in the right range. But if you need to adjust the viscosity of an ink upwards, it may be necessary to adjust those polymeric components of the formulation, or use a higher molecular weight polyethylene glycol as a viscosity modifier. Humectants, as we said before, prevent the water loss and inhibit the formation of a hard crust on the surface of nozzle plates. These work by binding to water molecules using hydrogen bonding. And the typical sorts of humectants might be glycols, glycerol. So here's an example of a generic inkjet formulation. So you've got typically 2, 3, 4, 5% colour in your formulation, proportion of water miscible solvent very often, such as diethylene glycol, a humectant such as glycerol, 2-pyrrolidone. 2-pyrrolidone can also be a solubility enhancer. The surfactant that we mentioned before, just 1 to 2% maximum of surfactant in there. A biocide, that example there's is benzisothiazolinone, very typical biocide used. A buffer, and then just solvent. And here's an example just taken from a Canon patent of a few years ago. It's just a very simple but typical formulation. 4% pigment. The resin here is actually a polymeric dispersing agent, and that's used to improve the dispersibility of the pigment particles and also to help stabilize ejection in the thermal inkjet ink. You've got that glycerol, diethylene glycol we mentioned before, and then you've got a wetting agent. That's the E100 that we mentioned there. And again, this resin mentioned in this patent here is quite a typical kind of dispersing resin. So that's a low molecular weight styrene, butyl acrylate, methacrylic acid copolymer. And this example, as we said before, ink surface tension was tuned to 26 dynes per centimetre. So those are the basics of formulation. Let's move on to stabilization and stabilization mechanisms. We talked about pigment inks, and pigment inks are examples of colloidal formulations. And thinking about colloids, collisions are important. So there's a little bit of science here. Many inkjet inks do contain colloidal particles well under 1 micron in diameter, so a few tens of nanometers in fact. So these will be usually pigment particles, but they may also be polymers and very occasionally, depending on the formulation, emulsion droplets. Colloidal particles collide with each other due to Brownian motion, convection and gravity, and as they do so, this can result in aggregation or coagulation of the particles and therefore destabilization of the colloid. And there are two main ways of stabilizing dispersions of particles. So electrostatically, using Coulombic repulsion or electrostatic stabilization by putting a charge on the surface, or by putting a steric barrier to aggregation, so-called entropic hindrance, by putting, for instance, polymeric chains on the surface of those particles. In non-aqueous solvents, it's very unlikely that you're going to get charged surfaces, and so steric stabilization will be the dominant mechanism for stabilization. You build that in, electrostatic stabilization built in by providing a charged pigment surface by adsorbing charged species. Usually they're anionic species, and you may well, as a rule of thumb, measure the zeta potential, which is an indication of surface charge. A rule of thumb says you need 30 millivolts of charge zeta potential in order to give you a reasonable degree of electrostatic stabilization in inkjet ink. Steric stabilization, that's all about adsorbing long polymeric chains which protrude from the surface to give you that steric barrier. So these will be copolymers which have regions in them forming loops and trains, and other regions which bind tightly to the pigment surface. And very often you'll put those two functions, both electrostatic and steric, in the same molecule, so polyelectrolytes can provide you both of those mechanisms in one dispersing agent. Time briefly, just to talk very briefly about performance and testing. So on this slide you'll see summarized some of the sorts of testing and evaluation that you may need to do during ink development. So during ink development itself, you'll be measuring properties such as pH, viscosity, surface tension, contact angle, particle size, zeta potential, storage stability. You'll need to assess operability, so drop formation, testing under extended printing times, looking at restart performance, looking at how the ink performs when the ink head is open to the elements, looking at the potential for nozzle clogging, carrying out print tests, third category of tests, so you'll be looking at color properties, at reflected optical density, at the bleed of ink from one area of color to another, strike through, does the ink go through the surface, looking at image quality, looking at whether you've got an even or a mottled surface, and all kinds of fastness properties as well. So let's summarize the sorts of things that we need to know. You need to make a choice of dye or pigment. You'll need to understand the function of the additives that you're putting in there. You'll need to understand stability mechanisms that may be operating in your ink. You'll need to understand what's happening with the substrate and the end application. You'll need to be able to measure and understand performance parameters such as formulation, jetting, and image quality. Barely had a chance to mention, of course, that there's a lot of IP, there's a lot of patents out there, so you'll need, when you're developing an ink, to be aware of IP issues. Everything I've said so far today, we've had a very short amount of time. I've concentrated mainly on water-based imaging inks, so using pigments or dyes, but of course these principles are also applicable to the more novel and modern non-imaging inkjet applications, which David mentioned at the start. So if you'd like to learn more, then as David mentioned at the start of the webinar today, we will be holding a one-day training workshop to pick up on some of these things that I've talked about today in much more detail on the 9th of June. You can see a web link there. You'll see our website and email addresses below. Using our associate partner, Mark Holbrook, to help us take you through in much more detail the formulation of inkjet inks. Over to David.
Thanks, Jim. In 30 minutes there was an awful lot to get through. Everybody's remain muted. We have got a few questions in, and we're not going to be able to take all of those, but what we will do is we'll send out answers to all of the questions to you, but we will take one or two. Jim, can you see the questions?
Yeah, I'm just starting.
One of the questions, I know, one of the questions talks about a copy of the talk. Yes, all the attendees today and all those who registered but couldn't quite make it will get not only a link to the recording, but also we'll get a PDF of all of the slides that were presented today.
Yeah, there's a question coming in here. Are constraints on polymer components dependent primarily on nozzle size due to potential blockages? Obviously, rheology surface tension will be affected by their inclusion, but surfactants could counteract this. Yes, so nozzle size is important, but the nozzle size is much bigger than a polymer molecule. So constraints on polymers may be, for instance, the rheological properties, also the thermal properties. If you've got a thermal inkjet, some of the polymers may degrade in a thermal head, or they may degrade under shear. So more normally the limitations are due to the nature of the print head, I would say, rather than the potential blockages due to the nozzle.
Do you want to take a brief comment on UV cured inks, Jim, as the last question before we finish today?
Yeah, so I'm just looking at that question now. UV cured inks, yes, that's another type of ink where the ink is then bound to the surface during the UV curing process. Advantage or disadvantage, it's reactive chemistry. So you've got to be a bit more careful in terms of the ink formulation, that you don't want that UV reaction happening within the ink. You only want it to happen on the surface. So you've got to be much more careful about the formulation because of that potential for reaction. Okay, I think that's it.
Okay. Yeah, I think we've overrun slightly, but they've been good questions. You will get a copy of the recording. Everybody here will see details of our next webinar, which is on the 23rd of June, which will be powders, granules and tablets, and we'll leave it there, and there's a link there to our training and events. So just want to say thank you all for your attention, and if you have any further questions, please email to info@iformulate.biz. Thank you very much, and goodbye.